Hello and welcome everybody to a new video. In this video we're going to be making this little device that you see in front of you, which is an ESP32-Powered EPaper weather display. So there's a whole bunch of new to me technology used in this, and it was a ton of fun to build, so stick around if you want to see how I made it. Okay, got all the parts here for the new project. I have an 18650 lithium cell. I've got a little small e-ink display. Have an ESP32, a charging module for the battery, and my custom switched power regulator module. So this is all I need pretty much for the entire thing. Whole thing we're going to be doing a little weather display thing. It'll connect wirelessly with ESP32 over my Wi-Fi, pull weather data, render it on the screen. You'll be able to turn it on and off with the power supply regulator. Be able to charge the battery with this little module, and that's the whole thing. Because it's battery powered, it'll be portable, move it around the house, have a little weather display. I'm not sure how useful that actually is going to be, but the whole deal is basically that I just want to play with some stuff I've never used before. I've never used an ESP32, never used an e-ink display, and never used one of these battery charging modules. So it'll be a lot of new stuff. Basically, me to try a whole bunch of new stuff, put it all together into a project. Hopefully it'll be a little template then that I can use for doing further battery powered, wireless IoT home stuff. Also, we're going to try run MicroPython on the ESP32, which is an environment I've never tried before for embedded programming. So yeah, that's it. That's what we're going to do. First thing I'm going to do, I'm going to get this wired up, make sure it works, make sure I can charge the battery, and make sure it works with my little power regulator. And then I'll probably try and set up a MicroPython environment on the ESP32, and then go from there. Integrate it with the screen, get the whole thing working, and then I'll probably print a little 3D printed enclosure for the whole lot. So first things first, let's wire up this thing, get it working. The electronics for this project are pretty straightforward. The EPaper to screen is just a little module that you buy with some wires, and an ESP32 is a pretty self-contained little board, so there's not a huge amount of wiring involved in this. It's really just routing power to everything. And I decided that I did want to make this little wireless device, given that it has a wireless network connection to the ESP32, so I wanted it to be battery powered. That's really the only complexity with this project, is having the battery charger built into the whole thing. I was designing a little board that would have the battery charger on it, and then also was going to integrate my switched power supply circuit into it with the voltage regulators, but I decided that was actually overkill, considering that the modules exist readily available to do the charging. So all I really had to do was then connect that up to my switched power supply, and that's it. Regulation done, all sorted out with a little power switch. So that's the route that I went with. For the form factor of it, it just so happens that one of the little charging modules fits neatly underneath my switching power supply. So I've got a USB-C port underneath the little power switch, which makes for quite nice ergonomics at the end when you just have one little slot in your in the side of the case where you can plug in a USB-C cable, and you can also access the power switch, turn it on and off. Okay, so we got our little power board finished up. Battery goes in the little holder, which is just glued down to this. Got our power regulator in there, and our little charging board underneath it. So it's kind of just stacks in as a nice little package. This went together fine. There was one weird little quirk that I had where it took me a little bit of time to debug it. You might be able to see, it's kind of hard to see. There's a little resistor down in here that I've put in the connection. So I was connecting the output of this board directly to the input of my my switched regulator board, and for some reason I was getting this really strange behavior that I can't really explain, where the board was putting itself into protection mode, which is like an over current protection, or yeah, and I'm really not entirely sure why, because it was only happening when I would turn this off. So yeah, I'm not entirely certain why, but what I ended up determining was it didn't happen when I connected everything up with jumper wires. So that was suspicious. I thought maybe there was a short somewhere, so I pulled everything apart, resoldered it, a bunch of that, and nope, same problem was still happening. And then I thought, fluke of flukes, with jumper wires I measured some resistances and found that I was introducing a couple of hundred ohms of resistance by adding in jumper wires. So I added the smallest resistor I have, a 220 ohm resistor, between the output of the charging module and the input of the power regulator, and lo and behold, that fixed everything. So yeah, not entirely certain why that's happened. Didn't expect it, but hey, useful to know. If someone can give me a breakdown of exactly why, I suppose it's hard to know without seeing the exact diagram of this and the exact diagram of the charging circuit. Maybe that'll explain it. But anyway, we've got around it and it works. So take my battery and can stick it into the little battery holder here, which is a little bit tight. There we go, in place. And then I can turn this on and off. And yeah, the power light shows that it's doing its thing. I've checked all the pins. They appear correct or doing the right thing. And I can plug in a USB charging cable to there. And, ooh. Yeah. Oh, why is that not charging? Ooh. Maybe I broke something. Hold on, please hold. Okay, there we go. Take two. That worked. It was actually this. This happened to be connected to my Mac charger, which is doing its clever stuff where it tries to negotiate with the device as to what power delivery it can deliver, and was determining that it did not want to deliver power to this, but this is just a regular 5-volt USB-C charger, and that's working fine. And then while that's connected, I can also still power on and off the device, and yeah, that'll charge this battery and then do all of its good stuff. There we go. That's it. Very simple. Little neat package. I got these three little standoffs on top here, so they are going to be for another board to sit on top. And then this is where my main controller board is, my ESP32 board is going to sit on top of this, and there'll be a breakout header which will go to the EPaper screen. And that's it. That's the whole lot. Neat little package. So next thing, I'm going to get the ESP32 up and running with MicroPython. So there's another new thing to learn, and then I'll come back to wiring this up and getting the screen running. So yeah, that's that. Let's go and learn some MicroPython. Okay, let's start having a look at some of the code that I have set up on the ESP32, which is running MicroPython. So MicroPython, not going to go into massive detail about how you set it up from scratch. There's infinite amount of blogs and tutorials and stuff for getting MicroPython running on an STM32. I have mine connected up here to my computer. The basic bones of setting up MicroPython is you download a binary that is the MicroPython firmware, and you'll find compiled versions for different platforms. Specifically, I got this one for the ESP32. You need to flash that onto your microcontroller, and then your microcontroller is effectively going to be, every time it's powered up, it'll boot into and run this MicroPython environment, which you can then use to do stuff with, and that's like the layer that you'll then interface with. Again, I won't go into huge details on how to do that. You'll find loads of stuff to do it, but there's a script you can download. Pretty much, it's as simple as you download the binary, download a script, estools.py, and then that will do all the stuff for you. And from there, then there's just a few bits and pieces you need to know to be able to get up and running with it. So very straightforward. The part that's a little bit more interesting is how you can go about, setting up an actual sort of application that runs on it, and how you can deploy your code onto it. It's a little bit fiddly. So that's what I did here. I'll talk about that. So first things first, let's maybe connect to our board and see that running. So in my README here in the code, which link in the description, you'll find it. We've got a few things that you can do. So installing dependencies, flashing MicroPython, deploying the code, and then a debugging step too. So we're actually going to start with this debugging step because I've obviously done all of this already. So this screen is an application that lets you connect to a serial port at a specific baud rate, in this case specified here. So I know this will be different for you. This is what it happens to be for me on my computer. So I can run that in my terminal, and oh, didn't work. Okay, why did that not work? Maybe my board, might just unplug it and plug it in again. Let's try that. Okay, let's try again. Yeah, there we go. Okay, that's connecting, and I just Control C just to stop the code that was executing. So when you connect to the REPL here, which is the read, execute, print loop of the MicroPython environment, it boots into your main file that is set up for your application and it starts executing it. And it just so happens my main file code is an infinite loop that will just run forever. So I don't want to execute that because I want to actually execute some commands and stuff here. So I just killed it. So yeah, this is a standard Python terminal that you might be used to if you've done Python before. You can type in Python code and it will execute it in normal way. Very simple. What we can do with this now is we can start messing around with some of the code that I've written, which kind of will give you a little bit of an idea of how some of this stuff works. So two things to happen straight away when your chip boots with MicroPython. There's two files that are important. You've got boot.py and main.py. So boot.py is the first thing that gets executed when the board starts up. So this is sort of where you would put a lot of setup stuff. So you put in here, for example, in my one right now, I have code in here that goes off and connects to my Wi-Fi. So we can do that. Why not? Let's do it. So if I go, so I've got some stuff in here. So the imports in here are basically, standard Python import stuff. So I have my code written up here. This is a Python module, weather display module, and it has other sub-modules inside it. And importing all this code just works the same way it does in normal Python. The files get copied over onto the board, and then they're accessible in the exact same way. So MicroPython will do its module parsing in the exact same manner. So first thing I'll do, we're going to connect to the Wi-Fi. So I can go import config, which I'll need, and then copy this. Yep, and then we can connect to our Wi-Fi. So let's try that. There we go. Now we're connected to my Wi-Fi. Quick and simple. So if we go into the connect to Wi-Fi function, you see this is defined in this weather display utils file. And yeah, it just has some really simple code. It takes an SSID and a password as parameters. And yeah, just tries to attempt to the Wi-Fi network, connect to the Wi-Fi network. You'll find all this in the docs for the ESP32, all the specifics of what this is doing. So a quick note, the SSID and password are secret effectively. You don't want to necessarily, well, the SSID isn't really secret, but the password is. You don't want to just be publishing that, especially don't want to commit it to a repository on GitHub. So what I have here is I have my config.py file, which is just a normal Python file that has these variables defined in it. So you can access them like this. I'm not going to open it because it is a secret, but what you see is I have this template. So you'll see this is how you specify them in this, and this is effectively just like an environmental variable thing. Normally you'd use envvars in a real Python application, but does not quite support it in terms of the MicroPython environment. So this is just a kind of a hacky way where I have this template version so people can see what to do, but in the real thing you need to remove the word template, have a config.py, and have your actual secrets in that. So this isn't going to go anywhere. It'll only go onto the board, and that's it for the deployment. What else then? So I guess we can look at my main file then. So yeah, I said there were two files at the very start, boot.py and then main.py. So boot.py will execute, and it should be sort of your startup config stuff. And then main.py is basically your application. So this is what you want to run. If you put a while true at the very top, it will just do forever. And it's just a loop that the application will run in forever, which is very typical of a lot of microcontroller applications. You want to kick something off and you just want it to go until it powers down or whatever. In this case, I have set up that it will check the time that's passing, and every 15 minutes, every 15 minutes it will go and fetch weather data from an online service, and it will then print it out. So what will happen in real life is this will, when I get it written, is it will put that weather data onto the EPaper display that's going to be connected up to the whole system at the end. For now, let's just grab some weather data. So I can do the same thing I did earlier. I can import the module here, and then I can go and run this to fetch some weather data. And let's see what it does. Fetching weather data. Fetching weather data. There we go. So that's the weather in my local area right now. So this specific service, it's wetter, wttor.in, and it is a free weather service thing. It has a whole bunch of different stuff. It has a JSON API you can connect to, and it uses your IP address to return the current weather. So from here, it's visibility 10, whatever that means. It's sunny in my area, and what else have we got? What's the temperature? Where's the temperature in Celsius? So I understand what it means. Feels like 40 Fahrenheit. I don't know what that means. Temperature 6 degrees Celsius. Feels like 5 degrees apparently. Yeah, there we go. Just getting some weather data. So yeah, I guess the last thing to really talk about. So it's all pretty simple. This is basic Python stuff. If you know a little bit of Python, this isn't too complicated. One note is I have in here these garbage collector calls. So this is something that might be unfamiliar to you if you're a Python person, but not necessarily a low-level language person. I've never done a language that requires manual garbage collection before. You won't really know this too much, but Python is a high-level language and it has a garbage collector, but we're still working in a really low-level environment with a tiny, tiny, tiny amount of memory, and you will get out-of-memory errors using Python in this environment. So Python isn't necessarily optimized for memory consumption, so it's got a relatively large footprint. So you do need to be a little bit deliberate about when you call the garbage collector. What I was finding while doing these network requests, so this is fetching the data from this endpoint and then parsing out some data, a document as JSON, and then putting it into an object for a response. The JSON document that's getting returned here is actually quite large. The payload is pretty big, and yeah, it's in a modern computing environment we wouldn't even consider how big that payload is, but on a microprocessor environment that actually makes a difference. So yeah, you have to do a little bit of garbage collection work here just to make sure that you won't run out of memory as you're doing continual loops of this application. So yeah, last thing I guess is some of the scripts I have in here. So yeah, these aren't anything wild. They're literally just hacked together to save me some time while working on things. The deploy script is probably the most interesting one. Or shell. This is a really valuable tool. You should know about. I'll throw a link in the description. If you're working with MicroPython, or shell is a tool that sets up like an interactive shell type environment on your board. So if you're using an actual Pi board, which is the type of which is the microcontroller specifically designed for MicroPython, they usually mount to your computer as like a USB drive as well, so you can literally drag and drop your files in to deploy stuff, which makes it very quick and easy. ESP32, which will run MicroPython, won't mount in the same way because the USB controller isn't set up to be able to handle that type of to be able to identify the board as that type of device to your computer, so it won't ever work like that. Or shell gives you this ability to be able to basically open up a terminal window into it and also copy files into it with a script, which is exactly what this cp command here does. So you tell or shell, this is your serial port, this is your baud rate, give it the command and tell it what files to copy over, and that will do that then for each one. I think you could do this in bulk. I literally copy pasted these one after the other because it was just the quickest way to get to the thing. So it's kind of slow because it connects to the serial port for each one of these, but it's reliable and it updates your code in place each time, which is really handy. So this will deploy all of my code files to my microcontroller when I run this script, which is quite handy. So it means you can update your code easily enough. Is there anything else to say on this? I don't think so. I think that's pretty much everything I wanted to cover. Yeah, if I think of anything, I'll mention it later. I'll probably come back to some code a little bit later on, maybe when I figured out how to actually work with the EPaper display. I might talk into a little bit of detail about it because the EPaper display uses an SPI communication protocol. So actually what I'll probably do is I'll probably talk about the comms protocol more than the actual code specifically. I might show the code somewhere, but in any case, when this project is finished, you'll be able to go and have a look at all the code for it on GitHub. So yeah, link in the description for that. You can go check it out. For now, I'm going to go off and I'm going to figure out exactly how to make this EPaper display work with SPI using my microcontroller. So that's the next thing for me. It'll be but a few moments for you and you'll see the next bit.
Okay, we're back. We've made some progress. Can officially say we have our EPaper display working. You can see that there. We've got it showing some text on the screen, which is exactly what we wanted, and that is actual weather data. So that's pretty cool. So the code has changed a good bit. I'm not going to go into massive detail about exactly how the code works, but I'm going to show you, point to some things, give you some broad overview, and talk a little bit about how the actual EPaper screen works and the interface that you need to make it work. So yeah, let's jump in. So yeah, first part, you see over here in this dock I have open. So the EPaper display that I'm using is this Waveshare 2.7-inch EPaper hat. So they call it a hat because it's meant as a hat for a Raspberry Pi, hence this port on the back of it, but you can also just use the little like cable that they break out here to interface with it, which is just fine. So this link here I'll throw it in the description, but it has tons of detail, all the specs, everything you need to know about how to get up and running with this. But what I found actually more useful than just this, so one thing that is in this that's really useful is there's loads of examples for different hardware that you can interface with it, and they also have links to sample code, so that's really handy, and I'll come back to the sample code a little bit later. But also in here you'll find a link to this doc, which is the full-on proper product spec sheet, it's called data sheet for this device. And yeah, the first thing I want to talk about a little bit is the interface that you need to communicate with this. So to communicate with this device, you need to communicate over SPI, which is the serial peripheral interface. So the datasheet has all the details about what SPI is and how it works. Basically, you need a couple of wires that can communicate with the device, which sets up this kind of this pulsing frequency, which sends individual bits serially. And then you also need some other wires that can do flip on and off different pins that do different things as well. Won't get into detail about that, but if you read the spec, you can understand it. It's quite straightforward. The main thing, though, that you'll get out of the datasheet, which is quite important, is if you scroll down a bit more past this, you'll find this commands table. So the commands table basically gives you everything that you need to know about how the SPI interface actually works with the device. So what this does, SPI sends 1 byte at a time serially to the device. And based on this commands table, this interprets those bytes and does different things in the device. So you've got command bytes and you've got data bytes. So there's a pin called CD, which command data, and that flips on and off to tell the device whether it's listening for a command or listening to data. If it's a command, it'll try and match it to some command in this table, which these are the individual bits that'll tell you what they actually are, which then tells you what byte to write to the device. And then depending on what command it gets, it knows what to do with the data that you might subsequently send it to. So, for example, if you want to write to the memory of the device, which is how you get it to display something on the screen, you'll send the I want to write data to you, and then, or I want to write to your memory command. It then knows what to do with the data you're about to send it. You send all the data, and then it knows that it'll store that in its memory. If that's a little bit obtuse, don't worry too much. I'll show you the code. It's not super complicated to set that up. You don't massively need to understand it as long as you can execute the code or understand the code. This just works. So don't worry too much about it. So yeah, with that said, let's have a look at what the code does for that. So here's my main function. It's a little bit different than the last time we saw it. I'll just talk through quickly some of the differences. So last time we had a main loop in here, which is like an infinite loop that would keep going to do stuff. I've actually abandoned that since. I'll show you why. So let's just go through what this does from the top down. The device boots up. It connects to the Wi-Fi. It then goes and fetches the weather data. It formats the weather data in a specific way that is needed for the device to understand it. It then boots up the device. It configures it. It sends that data. It tells the device to go to sleep, which is the EPaper screen. And then it itself goes to sleep for 15 minutes, the ESP32. This is the magic that means that you don't need to have an infinite loop, because the deep sleep command will put the device into a sleep mode for this timer. Then once that time has elapsed, the device actually soft reboots itself, and so it'll then reload this code from the start again, and it'll run through this exact thing every 15 minutes. So that's why you don't need an infinite loop, because it's built into the boot cycle that you have because of using deep sleep, which is very handy. Deep sleep also then means that it will consume
fractional amounts of power while it's asleep, which is good. So it means if you're connecting to a battery, it should last much longer. And the EPaper screen itself also should use no power once it's asleep as well, or very little power once it's asleep. And this isn't connected to anything right now, and as you can see, it still has the text on it, which is the magic of EPaper. So that's pretty cool. So I won't go through connecting to the Wi-Fi and fetching the data. We've already looked at that before. I will talk about the generating data, but talk about that in just a second. First thing I'll do is let's have a look at how the EPaper setup works. So this is a class that I've written. So if you go in here, this looks a little bit complicated, but it's actually really not too bad. This code now I wrote this, but it's mostly cobbled together from stuff that I found in the example code from Waveshare themselves. There's also some libraries that do some porting of stuff over to MicroPython. I think this originally was all written mostly in C, so if you look at the Arduino code for this, it's almost identical, but this is just ported over to Python, so it's not too bad to understand. All it's doing, it sets up the EPaper. We'll initiate the class first. First thing it does is it connects to the EPaper with SPI, or sets up the SPI bus to communicate with the EPaper, sets up the pins for it, and then sets up some other pins that you need. So this is the CD pin that I mentioned earlier for telling it whether it's a command or data, and it does some other stuff. It then defines a few things. Defines how to send a command and how to send data. So we flip some bits on and off that are connected by different wires, and then we do an SPI write, and that's it. Same with the sending data. Has some other functions, a wait function, which checks the busy pin on the device if it needs to wait and hang on if it's doing something. Has a reset function, which is a reset pin on the device. You just pulse it high, low, and then it will reset the device. But the real meat comes down here. So this is the part that I needed to use the reference code for. I figured SPI is just SPI. It's just a send data, receive data type thing. But knowing how to configure it, this is where I needed the sample code, because the datasheet doesn't do much to tell you exactly what you're doing here. So this is just I can't tell you why you have to do this. I don't know exactly why this is the set of steps you have to do in specific. There's two versions of this board as well. There's a V1 and a V2. I happen to have the V2. If you have the V1, there's a similar config step, and they're all completely different commands. Again, don't know exactly why they are those commands, but this code is provided from Waveshare, so I'm assuming they're telling us this is how you should set up the device. So yeah, this is what we do. It sends some commands, which internally does some stuff. To me, it seems, I guess it's straightforward enough what this is doing. It does a software reset. It sets up addresses for RAM, which is a pretty common thing to do with microcontrollers. You tell it where 0 is, and then it knows how to go from there in memory and stuff like that. And it appears to put it into a data entry mode, which I assume it means that it can receive commands and things like that. So yeah, that's about it. The next thing then that is important is how you actually write to it. So the way this specific device works is you write to the memory of the device. So you say, so you're given, okay, should probably talk about a little bit about how the display works now, because that's also the next thing is going to be a little bit interesting to talk about. So the way it works is there are 264 lines on this screen. So 264 pixels down the way and 176 pixels across the way. If you divide those by 8, which is 1 byte, you'll get 22 bytes across and 33 bytes down. So that, if you multiply those together, you get 726. So that's the amount of bytes of memory that represent every pixel on the screen. So for every bit in that 726 bytes, going from the top corner here, this top corner of the screen, across and then down, so it scans basically across. See, it goes like 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, moves down one line and then comes back to the start and goes across. That is how you write data to the screen, and that is exactly reflected in the memory of the device. So down here, what this command does when you're writing to the device, I give it this frame buffer, which is just an array of bytes, 726 bytes. Then I write a command which says to the device, I'm going to write to your memory now. The device goes, cool, you can write to my memory. And then it knows that all of the data I'm going to send it after this, which is 726 bytes worth of data, it will write one at a time, and it will store it into its memory. What it then does is, so you do this, so you write it to the data. Once that data is written, you need to refresh the display. So I have a function up here that does that. You come up, refresh display, sends two commands, which basically tell it what to do. So they say, refresh your display, and it will then internally, it will read those bytes from memory. You'll see the screen flashes, and then it writes the new data, and then the screen flashes, and then you'll see the new data on the screen. And that's it. That's how it works. I feel like I kind of glossed over that a little bit. I would say step through this, have a look at the data sheet, convince yourself that what I'm saying makes sense, and then, yeah, you can go from there. Okay, so up to now, all I've told you is basically how individual bits actually get written to the screen. I haven't told you how you get text. So this is where I had to do a little bit of thinking. This is where it took me the longest part to actually figure out was how to get the text to render nicely. So what I determined was, well, I need a character on each on the screen. So I decided that my characters, so that you could read them quite clearly, because it's a small enough screen, were going to be 16 bits by 16 bits. And that's what each of these characters are. So what that gives me, if I decide a character is 16-bit by 16-bit, that means that I've got, that means that I have 22, or I've, these are your thoughts, Ian. I have 11 characters across and 16 lines down. It's actually 16 and a half, because you remember I said there's 33 bytes. But I've said I need 16 bits per character, which means I'd have half a character at the bottom. So effectively I have 16 full lines down the way and 11 characters across to play with. And that's how many characters I can write. But I still need to know what exact byte I need to, or what exact bit I need to write at the exact time across the way. So how do I do that? So that's where this formatter comes in. So the formatter, you can see down here, so you might, if it's, not sure if it's easy to read this or not, but you've got the characters that are on the screen there. You can see I've got like, it's the weather condition and then temperature, wind, etc., down the way. So I have that defined here in the code. So this is 11 lines, or sorry, it's 16 lines of 11 characters each. So these are a bunch of blank lines, and then I've got the ones that actually have the information in them. The code basically just pads them out if they're not 11 characters long, so that there's always 11 characters, which gives me my, when you process every character in here, you get the 726. And then what we do is we run it through this algorithm up here. And what this algorithm does is it goes through every line, that will be every bit. It figures out what character we're in as we go across it, and then it knows how to pull out which individual byte it's going to write in which order so that it can represent the correct characters. I realize that's totally maybe not intuitive to some people, but if you go through this, you can run this code just on your laptop. You don't have to run on the microcontroller. You can get it to like output hashes on your screen, and you'll see how it scans the characters and makes up the right things. But you still need to know, well, what pattern actually makes up the character that I'm going to write on the screen? Because it's, I've said it's a 16 by 16 bit, so I need some reference that is like an A is this bits. This is the bit pattern for an A. So where that comes in is this font thing here. So if we go into this font that I've defined, this is how I defined it. So there's a tool that generated this. I'll talk about that in a sec. But basically what it is this is the ASCII code. So this is the basic ASCII table. This is the ASCII code for it. And then this is all of the bits that make up each character. So this is a space character. So it's just all zeros, just a blank space, nothing there. These are bytes. So that's one byte, which is 8 bits each. So that's 16 bits. And then there's 16 of these the whole way down. So that's your 16 by 16. And then depending on the values in these are all written in hex. Depending on the values in them, you're going to have on, off, whatever. And then as you scan through that shows you what the shape of the character is going to be. And we use this reference table then to write the characters. Getting to this wasn't super easy. I had to write a tool up here, which I've called font. So you can go to the README in here and I'll show you a little bit of how you do it. I use this tool, which is really great. There's a GitHub user STMN, and they have this font to bitmaps tool, which is really cool. You give it a font true type font, and it will spit out a bitmap image of a font, which you can see here. So this is the Press Start 2P font. And so here's the actual bitmap image. It's a PNG. You can see you've got it's a transparent background with then the colors for each font. Then I wrote a really basic algorithm, pulls in the image for the font, loads it up, chunks up each one, and generates, like, it checks for the brightness of the pixels, zeros and ones, and generates the 16-bit values for each of them, and then basically spits them out, pretty prints them out into a file. So I generate a hash or a dict inside Python, and then pretty print that out to a file, which is these text files that have it in it. This is super janky, but it works. This was the best tooling way I could see to get the code into a format that works. So if you're a software developer, don't at me, because I know this is hacky, but it works. Doesn't matter as long as it works. It's only a hobby. But anyway, I realized this last bit, I've kind of gone a bit off the reservation. I love this part. It sparked the part of my brain that adores advent of code, where it's like solving little algorithmy, loopy type problems and doing this data representation stuff. If you're not into that, hopefully you can just use this code. Maybe you don't actually have to deeply understand it. There's also libraries that just do this. I wanted to do it from scratch because I thought it was really interesting. But if this doesn't spark anything in you, go use a library. You do you, bro. Perfectly good way to do it. So yeah, that's it. That's what I want to talk about with this. I've just realized how long I've been talking here. I didn't intend to talk this long on this. This video is going to end up being so long. But thanks for watching this far so far. I promise, I think this is the end of all the codey bits. The thing is done, basically. All the functions work. I'm pretty happy with it. Next parts are just, I need to wire up the final wiring for it so it all sits together with its power board, and then do some 3D printing, put it all in a box. Project's done. So hang on a little bit longer. You can see that stuff, and then we'll have the final product at the very end. Thanks for watching this far, guys, and let's stick around to see the rest of it. Okay, so we have our final electronics here. This is all wired up. It's not final yet. I still have to just mount some of these things together. The battery was hot glued down here. I will probably super glue it, hold it in place in a second. And these two boards sit one on top of the other, but I've just broken it out just so you can see all the parts to it. Very quickly, we have our battery, our 18650 cell. We have our power board, which has my custom power supply with a switch on it. It's got a USB-C battery charging port there. That then is connected to this little carrier board. This carrier board has my ESP32 mounted on here, and it's got some pins broken out which connect to my little screen. That's it. That's the whole lot. So when I've packaged all this up to go into the 3D printed enclosure, this will be in here. This board will be on top of it. So this will be one neat little package, and then the screen will be attached with the wires. So I can mount this however I want inside the enclosure, and have this mounted somewhere probably down the bottom in like a base, and then the screen will be like that, an angle or something. Figure it out. But for now, let's flick the switch, power it on, and let's see if the screen will do its thing. So power on, power. That's a good sign. So now this is going off, connecting to the Wi-Fi, calling out to the weather service. There we go. That's the update. So the eagle-eyed among you will notice that what's on this didn't actually change. That's because the 5:29 p.m. or 5:49 p.m. is the last update that the weather service has. So it'll just return you the same update again until a new one is fetched. And so now this device has gone to sleep, and it'll stay asleep for, and the screen will both stay asleep for 15 minutes, and then it will wake itself up again, reconnect to the Wi-Fi, call out over the network, grab that data, refresh the screen, and that's done. And it'll do that every 15 minutes. So that's pretty cool. We've gotten to a big milestone. All of the individual parts are working. We just have to put them in a nice little box. And then that'll be it. They'll have this nice, cool little wireless weather display I can move around my house. So that's pretty awesome. Um, right, let's go do some CAD. Have to design up the 3D print enclosure, print it, put it all together, and then we're done. This is one part of the project that I'm not super happy with, and that is my mechanical design. So I had this idea of making this in two parts, a base piece where most of the electronics will be housed, and then a slightly angled bit for the screen, just to make it a little bit easier to see it if it's sitting on a desk. And it turned out way chunkier than I'd liked it to be. So it's just a big piece. I'd like it to be a lot smaller, to be a bit neater. As I'm thinking about it now, there's definitely a lot of wasted kind of dead space inside the shell that I've made here. So I could definitely make this smaller and make it neater, make it look a bit better as well. There's a Thomas Sandlander video that was recently put out where he made an enclosure for like an air sensor thing. That actually just pinged in my mind after I'd made this, and his system is almost the same kind of size, but it's just a way nicer form factor, and it would look way better if I had done something like that. So, but hindsight 2020 and all that, this thing works. It got the job done, and it doesn't look terrible. It doesn't look amazing, but it doesn't look terrible. So, yeah, that's it. It's a very simple design. Two halves goes together in a shell with some threaded inserts stuck in. Yeah, just a little bit of 3D printing, and that's really it. Onto our final assembly now. I'm not going to lie, this was an absolute pain. So not only am I not so happy with the visuals of this design, it seems that I designed it in a way that made it very, very difficult to put together. You'll notice from the very start of this that the base electronics are already fitted into the bottom of the case, because that was a real nightmare to get them torqued up in place. So yeah, not a great design all around, but I skinned my knuckles a little bit and got there. So that's all that matters in the end, is that it actually went together and it holds together solid. So yeah, but definitely not my finest mechanical design ever. So there we have it. This is the end of the project. This was a really, really fun one to do. I learned a lot doing it. I touched a load of new technology that I'd never used before. I'd never used MicroPython. I'd never used an ESP32. Never used one of these EPaper displays. And yeah, just a whole lot, loads of learning and lots of really fun stuff. And at the end of it, it worked really well, and it is now sitting on my desk, and just is a fun little thing to have. So really happy with how this one turned out, and yeah, this was really great. This has been a long video, but if you managed to get this far, big respect to you. Thank you very much as always for watching, and I will see you in the next one.